Recollect again that duct insulation serves one or both of the following purposes, namely 1. Prevention of condensation on the duct's outer surface, and 2. Reducing heat gain by conditioned cold air flowing through the duct. In this lecture, we address insulation towards this second objective, that is ensuring that the heat gain by the conditioned air in the duct is within acceptable limits. In this lecture, we review an office air conditioning system in which the entire supply duct network is installed in the plenum above a false ceiling, and the return air at about 75 degrees Fahrenheit flows from the rooms directly into the plenum. The conditioned air at the AHU cooling coils is at 55 degrees Fahrenheit dry bulb, and we would require the heat gain all the way up to each and every room to result in a temperature rise not greater than 2.5 degrees Fahrenheit. In this example, there are two AHUs generating the conditioned air at 55 degrees Fahrenheit. Please don't worry if you do not see things clearly on this slide, since it is not important for the problem we are trying to solve. Let us select the longest duct, which is from AHU2. This duct has 9 sections designated section 01, section 12, etc. all the way up to section 89. Shown on this slide is the chart that we will use for finding the temperature rise per 100 feet of a bare rectangular duct. Using the chart, we first tabulate the data pertaining to section 01. We now move on to section 12 and plot the data pertaining to the same. Here we have tabulated the data pertaining to all the 9 sections. Notice that the cumulative temperature rise is unacceptable in sections 5, 6 onwards, since the design permits a maximum of 2.5 degrees Fahrenheit increase over the entire duct. We will now proceed to calculate the insulation required. The cumulative rise allowed is 0.125 degrees Fahrenheit, while without insulation the cumulative rise is seen to be 0.3216 degrees Fahrenheit. The U factor value required is calculated using the formula U equal to T1 minus T2 multiplied by 1.1, where T1 equals cumulative rise without insulation and T2 equals the cumulative rise allowed. Using this formula, we calculate the U factor required to be 0.22 BTU inch per square feet per hour per degree Fahrenheit. If we decide to use glass wool as insulating material, 25 mm or 1 inch thick glass wool is adequate as shown on this slide. In the next lecture, we will focus our attention on pipe insulation. See you in the next lecture.